Ladies and gentlemen, I'm Yang Yi from Beijing Institute of Technology, and it is my great honor to present our recent work, Privacy-Preserving Cooperative Online Matching over Spatial Crowdsourcing Platform. The presentation contains 7 parts. First, let me introduce the background and contributions of this paper. With the development of mobile internet and sharing economy technology, people's daily life has gradually become inseparable from spatial crowdsourcing applications, such as online taxi calling service, food delivery service, and express service. The main task of the spatial crowdsourcing platforms is to allocate suitable workers to complete the request on time, and to maximize the revenue or maximize the total matching number, etc. Most existing studies focus on the allocation for a single platform. However, the distributions of workers and requests within a single platform greatly affects the output of the system. Take Figure 1 as an example. Table 1 shows the arrival time of cars and users. Apparently, only 3 requests are allocated due to lack of available workers. In this case, the platform usually provides 2 choices. One is to increase the price of the request and the platform dispatch workers from further away. The other is to let users wait until there are available workers nearby. This will cause a reduction in user satisfaction and lose users. Fortunately, in real life, there are multiple platforms that provide similar services, such as Uber and Bolt. Also, some spatial crowdsourcing platforms, such as AutoNavi, choose multi-platform cooperation in real life. Therefore, several solutions based on multi-platform cooperation are provided to address the situation above. First, workers on other platforms can perform cooperation through bidding. However, it does not consider global matching situation, and workers have to focus on rushing for requests. Another existing research named cross-online matching enables the platform perform cooperation and assign requests reasonably. However, the above 2 cooperation methods are still impractical for widely use in real world due to the ignorance of data privacy protection. For example, the leakage of users' location will lead malicious platforms' net requests, and the leakage of historical information will lead malicious platforms' net workers. In the above situation, how to keep sensitive data private while retaining the benefits of cooperation is crucial. We need a privacy-preserved framework for cooperation among multiple platforms. In this paper, we propose a privacy-preserving cooperative online matching problem. PCOM solves 2 challenges. First, we designed a PCOM framework with theoretical proofs to protect sensitive data. Second, we propose 2 algorithms to solve PCOM problem, direct PCOM and selectable PCOM. Now, we briefly introduce a set of preliminary concepts in this paper. Here are some basic definitions. The definitions of request and worker are widely used in the study of spatial crowdsourcing. There are 2 types of platforms, which can be represented by its request set and its worker set. Auto payment is a payment brought by cooperative request. We assume that the auto payment always smaller than the original value of the request. The revenue of the platform contains 2 parts, the local revenue and the cooperative revenue. Given these basic definitions, we can define the privacy-preserving cooperative online matching problem in this paper. The PCOM problem aims to find a cooperative matching result with the maximum revenue for every platform in cooperation, under the following constraints: time constraint, 1-by-1 constraint, invariable constraint, range constraint, and the most important part, privacy constraint. Before we introduce our framework, it is necessary to give some basic evaluation criteria, and we use these to measure the degree of privacy protection. Differential privacy is widely used in the fields of database query. We use this mechanism to protect any piece of data of any worker. Geo-indistinguishability is designed based on differential privacy. We use this mechanism to protect the precise location. Now let me introduce our PCOM framework and the theoretical proofs of privacy protection. We designed a framework for PCOM problem which contains 2 cases. When the request appears on the platform, Each platform first determines whether there are available local workers. If the available worker set is not empty, the platform performs local process, which is to assign suitable available worker using the task assignment methods. If there is no available local worker, the platform will send a request to cooperative platforms and perform cooperative process. Now let me describe the cooperative process in detail. To ensure the location privacy of the request, the local platform first perturb the location of requests and send the request to all cooperative platforms. Then each cooperative platform finds available workers according to the perturbed location and the constraints. The platform which have available cooperative workers use a differential privacy mechanism to estimate the auto payment and send it to the local platform. After receiving the auto payments, the local platform selects a cooperative platform with the smallest one for cooperation. The selected platform determines whether and which available cooperative worker to serve the request. Finally, the local platform releases the request with a precise location and perform matching offline. The above is the entire process of PCOM. Then we analyze the privacy of this framework. We prove that for each auto request, the framework satisfies differential privacy. More details are shown in our paper. Now let me introduce the first PCOM algorithm, direct PCOM. The main idea of this algorithm is to price the auto payment of requests directly based on all historical request information through a privacy mechanism. More specifically, when a request appears to a platform, the platform first finds an available local worker and perform local matching. If there is no available local worker, the platform performs cooperative process. The most important part of cooperative process is how to price the auto payment under the condition of protecting platform information. So in the PCOM algorithm, we designed a direct pricing algorithm to solve this problem. We choose the exponential mechanism in differential privacy since it has better performance and returning discrete results. The main idea of this pricing algorithm is to query the unit price that occurs most frequently in similar distance and calculate order payment based on the result and the distance of request. We set the utility function of the query returns to the logarithm of occurrences of every unit price, and we prove that the sensitivity of this function is log 2. Then we calculate the probability distribution of every unit price based on this formula, which satisfies exponential mechanism. Finally, we select query result based on this probability distribution and return auto payment. Here's an example. At 8:01, request R1 arrives at platform B. Then the platform B starts to implement the PCOM framework. It first performs local matching. At 8:01, there is one available local worker, so R1 is assigned to W1. At 8:08, R4 arrives at platform A. It has no available local worker and performs cooperative process. It perturbs the location R4 and sends to platform B and C. Assume that the privacy budget is 0.5. Take platform C as a pricing example. Assume that the unit price distribution in platform C is shown in table 1. Then we calculate query result probability distribution of each unit price. Assume that the algorithm selects 3.1 as unit price, and auto payment in platform C is 7.75. Assume that the auto payment in platform B is 10.5. Then the platform A select platform C for cooperation, and R4 is assigned to W5. However, there are some shortcomings of the PCOM algorithm. First, in the process of matching, the algorithm may assign too many local workers to perform the request with small value. This will lead to the loss of requests with larger price and reduce the revenue of the platform. For example, in the following figure, we assume that the revenue of request 2 is 9 and that of request 4 is 20. In the algorithm, R2 is assigned to W4 and the revenue of platform A is 9. When R4 appears, there is no available local worker and the platform has to find cooperative worker to finish it, and the platform A can only get 2 from request 4. So the total revenue of platform A is 11. However, if W4 does not serve R2 but waits until R4 appears, then the platform will earn at least 20. Therefore, the platform should allocate more high-priced requests to local workers. Second, in the process of calculating the auto payment, the algorithm ignores the preference of available workers of the request. Therefore, the probability of the request being rejected may increase, so the platform should consider the willingness of cooperation in the pricing algorithm. Now, let me introduce the improved method, selectable PCOM algorithm. The main idea of this algorithm is to filter requests by computing a random threshold and calculate the auto payment based on the acceptance probability. More specifically, when a request appears, if its value is larger than the setting threshold, the platform performs local matching. Otherwise, it performs cooperative process. Different from DPCOM algorithm, SPCOM returns the auto payment based on the expectation of auto payment through a privacy mechanism. Now, let me introduce the pricing method in SPCOM, which is called optimal pricing algorithm. We consider the willingness of cooperation in local platform and use the expectation of auto payment to set the price. The main idea of the optimal pricing algorithm is to query the auto payment that maximizes expectation from the historical data of available workers. For every auto payment, the utility function returns the maximum expectation, and finally, we select query result based on this probability distribution and return the auto payment. Here is an example. At 8:01, request R1 arrives at platform B. We assume that the threshold is 10. Since the revenue is larger than the threshold, so the algorithm performs local matching and assigns W1 to serve it. In 8:08, R4 arrives at platform A. Since the revenue is smaller than the threshold, the algorithm performs cooperative matching. Take the cooperative process in platform C as an example. At this time, there is only one available worker in platform C. The historical value and its probability distribution are shown in Table 2. Assume that 5.2 is selected as an auto payment. Then the request 4 is assigned to worker 5 with an auto payment at 5.2. Finally, we conduct a series of experiments on both real and synthetic datasets to evaluate the effectiveness, efficiency, and scalability of our algorithms. First, I will briefly introduce the experimental setup. We use both real datasets and synthetic datasets to perform the experiment. We compare our algorithms with the matching algorithm on a single platform and a state-of-the-art cross-online matching algorithm. We first evaluate the effectiveness of our algorithms based on 4 metrics: the total revenue, the total number of completed requests, the total number of cooperative requests, and acceptance ratio. These 3 tables are the results on the real dataset. It is obvious that our proposed privacy-preserved algorithms still maintain the effectiveness of cooperative matching under the condition of privacy protection. Compared to other algorithms, PCOM algorithms both increase the total number of served requests, and the response time and memory of 2 algorithms shows that they remain highly efficient. 4 variables are tested on the synthetic datasets in the scalability test, and the experimental results show that our proposed privacy-preserved algorithms still maintain the effectiveness. For the conclusion, in our work, we first propose a privacy-preserving cooperative online matching problem, which protects sensitive data during the cooperative matching process. We also designed a PCOM framework and theoretically proved that it satisfies differential privacy. Based on the framework, we propose 2 algorithms with 2 privacy-preserving pricing mechanisms. Extensive experimental results over real and synthetic datasets shows the effectiveness and efficiency of our algorithms. In future work, researchers can further discuss more privacy mechanisms based on the PCOM framework and effective cooperative matching algorithm that maximize the benefits of each platform. Thanks for listening.